The Moon is Earth's only natural satellite.
Its diameter is about 1/4 of Earth's, comparable to the width of Australia, making it the fifth largest satellite in the Solar System and the largest and most massive relative to its parent planet.
It is larger than all known dwarf planets in the Solar System.
The Moon is a planetary mass object with a differentiated rocky body, making it a satellite planet under the geophysical definitions of the term.
It lacks any significant atmosphere, hydrosphere, or magnetic field.
Its surface gravity is about 1/6 of Earth's at 0.1654 g. Jupiter's moon Io is the only satellite in the Solar System known to have a higher surface gravity and density.
The Moon orbits Earth at an average distance of 384,400 kilometers, 238,900 miles, or about 30 times Earth's diameter.
Its gravitational influence is the main driver of Earth's tides and very slowly lengthens Earth's day.
The Moon's orbit around Earth has a sidereal period of 27.3 days.
During each synodic period of 29.5 days, the amount of the Moon's Earth-facing surface that is illuminated by the Sun varies from none up to nearly 100%, resulting in lunar phases that form the basis for the months of a lunar calendar.
The Moon is tidally locked to Earth, which means that the length of a full rotation of the Moon on its own axis causes its same side, the near side, to always face Earth, and the somewhat longer lunar day is the same as the synodic period.
Due to cyclical shifts in perspective, libration, 59% of the lunar surface is visible from Earth.
The most widely accepted origin explanation posits that the Moon formed 4.51 billion years ago, not long after Earth's formation, out of the debris from a giant impact between Earth and a hypothesized Mars-sized body called Gaia.
It receded to a wider orbit because of tidal interaction with the Earth.
The near side of the Moon is marked by dark volcanic maria seas, which fill the spaces between bright ancient crustal highlands and prominent impact craters.
Most of the large impact basins and mare surfaces were in place by the end of the Imbrian period, some 3 billion years ago.
Although the reflectance of the lunar surface is low, comparable to that of asphalt, its large angular diameter makes the full Moon the brightest celestial object in the night sky.
The Moon's apparent size is nearly the same as that of the Sun, allowing it to cover the Sun almost completely during a total solar eclipse.
Both the Moon's prominence in Earth's sky and its regular cycle of phases have provided cultural references and influences for human societies throughout history.
Such influences can be found in language, calendar systems, art, and mythology.
The first artificial object to reach the Moon was the Soviet Union's uncrewed Luna 2 spacecraft in 1959. This was followed by the first successful soft landing by Luna 9 in 1966.
The only human lunar missions to date have been those of the United States Apollo program, which landed 12 men on the surface between 1969 and 1972.
These and later uncrewed missions returned lunar rocks that have been used to develop a detailed geological understanding of the Moon's origins, internal structure, and subsequent history.
The Moon is the only celestial body visited by humans.
Names and etymology.
See also, Moon mythology and art.
The usual English proper name for Earth's natural satellite is simply Moon, with a capital M.
The noun moon is derived from Old English na, which, like all *its Germanic cognates, stems from Proto-Germanic *mn, which in turn comes from Proto-Indo-European *nsis month, from earlier *mnt, genitive *mnesis, which may be related to the verb measure, of time.
Occasionally, the name Luna/Lun/ is used in scientific writing and especially in science fiction to distinguish the Earth's moon from others, while in poetry Luna has been used to denote personification of the Moon.
Cynthia/Sne/ is another poetic name, though rare, for the Moon personified as a goddess, while Selene/Selene/, literally moon, is the Greek goddess of the Moon.
The usual English adjective pertaining to the Moon is lunar, derived from the Latin word for the moon, luna.
The adjective Selenian/Selenian/ derived from the Greek word for the moon, cell, and used to describe the moon as a world rather than as an object in the sky, is rare, while its cognate selenic was originally a rare synonym but now nearly always refers to the chemical element selenium.
The Greek word for the moon does however provide us with the prefix seleno, as in selenography, the study of the physical features of the moon, as well as the element name selenium.
The Greek goddess of the wilderness and the hunt, Artemis, equated with the Roman Diana, one of whose symbols was the moon and who was often regarded as the goddess of the moon, was also called Cynthia, from her legendary birthplace on Mount Cynthus.
These names, Luna, Cynthia, and Selene, are reflected in technical terms for lunar orbits such as apollune, paracynthian, and selenocentric.
The astronomical symbol for the moon is a crescent, for example in M lunar mass, also ML.
Natural history.
Lunar geologic timescale.
Main article, Lunar geologic timescale.
Millions of years before present.
The lunar geological periods are named after their characteristic features, from most impact craters outside the dark mare, to the mare and later craters, and finally the young still bright and therefore readily visible craters with ray systems like Copernicus or Tycho.
Formation.
Main articles, Origin of the Moon, Giant Impact Hypothesis, and Circumplanetary Disk.
The far side of the Moon, lacking the near side's characteristic large dark areas of Maria, resembling how the near side of the Moon might have looked early in the Moon's history.
Isotope dating of lunar samples suggests the Moon formed around 50 million years after the origin of the Solar System.
Historically, several formation mechanisms have been proposed, but none satisfactorily explains the features of the Earth-Moon system.
A fission of the Moon from Earth's crust through centrifugal force would require too great an initial rotation rate of Earth.
Gravitational capture of a pre-formed Moon depends on an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing Moon.
A co-formation of Earth and the Moon together in the primordial accretion disk does not explain the depletion of metals in the Moon.
None of these hypotheses can account for the high angular momentum of the Earth-Moon system.
The prevailing theory is that the Earth-Moon system formed after a giant impact of a Mars-sized body, named Gaia, with the proto-Earth.
The impact blasted material into orbit about the Earth and the material accreted and formed the Moon just beyond the Earth's Roche limit of (2.56 R).
Giant impacts are thought to have been common in the early solar system.
Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system.
These simulations show that most of the Moon derived from the impactor, rather than the proto-Earth.
However, more recent simulations suggest a larger fraction of the Moon derived from the proto-Earth.
Other bodies of the inner solar system such as Mars and Vesta have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth.
However, Earth and the Moon have nearly identical isotopic compositions.
The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated.
The impact would have released enough energy to liquefy both the ejecta and the Earth's crust, forming a magma ocean.
The liquefied ejecta could have then reaccreted into the Earth-Moon system.
Similarly, the newly formed Moon would have had its own lunar magma ocean. Its depth is estimated from about 500 kilometers, 300 miles, to 1,737 kilometers, 1,079 miles.
While the giant impact theory explains many lines of evidence, some questions are still unresolved, most of which involve the Moon's composition. Example needed above a high-resolution threshold for simulations. A study published in 2022 finds that giant impacts can immediately place a satellite with similar mass and iron content to the Moon into orbit far outside Earth's Roche limit.
Even satellites that initially pass within the Roche limit can reliably and predictably survive, by being partially stripped and then torqued onto wider, stable orbits.
Natural development.
Artists' depiction of the Moon as it might have appeared in Earth's sky after the late heavy bombardment around 4 billion years ago, when its orbit was half as close to Earth and it appeared 2.8 times larger than today.
After the Moon's formation it settled into a much closer Earth orbit than it has today.
Each body therefore appeared much larger in the sky of the other, eclipses were more frequent, and tidal effects were stronger.
Due to tidal acceleration, the Moon's orbit around Earth has become significantly larger, with a longer period.
Since cooling and stripped of most of its atmosphere, both originating from its initial formation, the lunar surface has been shaped by large impact events and many small ones, forming a landscape featuring craters of all ages.
The prominent lunar maria were produced by volcanic activity.
Volcanically active until 1.2 billion years ago, most of the Moon's mare basalts erupted during the Imbrian period, 3.33.7 billion years ago, though some are as young as 1.2 billion years and some as old as 4.2 billion years.
There are differing explanations for the causes behind the eruption of mare basalts, particularly their uneven occurrence, mainly on the near side.
Causes of the distribution of the lunar highlands on the far side are also not well understood.
One explanation suggests that large meteorites were hitting the Moon in its early history, leaving large craters which then were filled with lava.
Other explanations suggest processes of lunar volcanism.
Physical characteristics.
The Moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth, due to gravitational anomalies from impact basins.
Its shape is more elongated than current tidal forces can account for.
This fossil bulge indicates that the Moon solidified when it orbited at half its current distance to the Earth, and that it is now too cold for its shape to adjust to its orbit.
Size and mass.
Further information, list of natural satellites.
Size comparison of the main moons of the Solar System with Earth to scale.
19 moons are large enough to be round, several having subsurface oceans and one, Titan, having a considerable atmosphere.
The Moon is by size and mass the fifth largest natural satellite of the Solar System, categorizable as one of its planetary mass moons, making it a satellite planet under the geophysical definitions of the term.
It is smaller than Mercury and considerably larger than the largest dwarf planet of the Solar System, Pluto.
While the minor planet moon Charon of the Pluto-Charon system is larger relative to Pluto F, the Moon is the largest natural satellite of the Solar System relative to their primary planets G.
The Moon's diameter is about 3,500 kilometers, more than a quarter of Earth's, with the face of the Moon comparable to the width of Australia.
The whole surface area of the Moon is about 38 million square kilometers, between the size of the Americas, North and South America, and Africa.
The Moon's mass is 1/81 of Earth's, being the second densest among the planetary moons, and having the second highest surface gravity, after Io, at 0.1654 g and an escape velocity of 2.38 km/s, 8,600 km per hour, 5,300 miles per hour. Structure. Main articles, Internal structure of the Moon and geology of the Moon.
Moon's internal structure: solid inner core, iron metallic, molten outer core, hardened mantle, and crust. The crust on the Moon's near side permanently facing Earth is thinner, featuring larger areas flooded by material of the once molten mantle forming today's lunar mare. The Moon is a differentiated body that was initially in hydrostatic equilibrium but has since departed from this condition. It has a geochemically distinct crust, mantle, and core. The Moon has a solid iron-rich inner core with a radius possibly as small as 240 kilometers, 150 miles, and a fluid outer core primarily made of liquid iron with a radius of roughly 300 kilometers, 190 miles. Around the core is a partially molten boundary layer with a radius of about 500 kilometers, 310 mi. This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the Moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine,
clinopyroxene, and orthopyroxene. After about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop.
The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements.
Consistent with this perspective, geochemical mapping made from orbit suggests a crust of mostly anorthosite.
The moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth.
The crust is on average about 50 kilometers, 31 mi, thick.
The Moon is the second densest satellite in the Solar System, after Io.
However, the inner core of the Moon is small, with a radius of about 350 kilometers, 220 mi, or less, around 20% of the radius of the Moon.
Its composition is not well understood, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the Moon's time-variable rotation suggest that it is at least partly molten.
The pressure at the lunar core is estimated to be 5 GPa, 49,000 atm.
Gravitational field.
An astronaut jumping on the Moon, illustrating that the gravitational pull of the Moon is approximately 1/6 of Earth's.
On average, the Moon's surface gravity is 1.62 m/s2, 0.1654 g, 5.318 feet/s2, about half of the surface gravity of Mars and about 1/6 of Earth's.
The Moon's gravitational field is not uniform.
The details of the gravitational field have been measured through tracking the Doppler shift of radio signals emitted by orbiting spacecraft.
The main lunar gravity features are maskins, large positive gravitational anomalies associated with some of the giant impact basins, partly caused by the dense mare basaltic lava flows that fill those basins.
The anomalies greatly influence the orbit of spacecraft about the Moon.
There are some puzzles. Lava flows by themselves cannot explain all of the gravitational signature, and some maskins exist that are not linked to mare volcanism.
Magnetic field.
The Moon has an external magnetic field of less than 0.2 nanoteslas, or less than 100,000th that of Earth.
The Moon does not currently have a global dipolar magnetic field and only has crustal magnetization, likely acquired early in its history when a dynamo was still operating.
However, early in its history, 4 billion years ago, its magnetic field strength was likely close to that of Earth today.
This early dynamo field apparently expired by about 1 billion years ago, after the lunar core had completely crystallized.
Theoretically, some of the remnant magnetization may originate from transient magnetic fields generated during large impacts through the expansion of plasma clouds.
These clouds are generated during large impacts in an ambient magnetic field.
This is supported by the location of the largest crustal magnetizations situated near the antipodes of the giant impact basins.
Atmosphere.
Main article, Atmosphere of the Moon.
The thin lunar atmosphere is visible on the Moon's surface at sunrise and sunset with the lunar horizon glow and lunar twilight rays, like Earth's crepuscular rays.
This Apollo 17 sketch depicts the glow and rays among the general zodiacal light.
The Moon has an atmosphere so tenuous as to be nearly vacuum, with a total mass of less than 10 tons, 9.8 long tons, 11 short tons.
The surface pressure of this small mass is around 310-15 atm, 0.3 nPa. It varies with the lunar day. Its sources include outgassing and sputtering, a product of the bombardment of lunar soil by solar wind ions. Elements that have been detected include sodium and potassium, produced by sputtering, also found in the atmospheres of Mercury and Io, helium-4 and neon from the solar wind, and argon-40, radon-222, and polonium-210, outgassed after their creation by radioactive decay within the crust and mantle. The absence of such neutral species, atoms or molecules, as oxygen, nitrogen, carbon, hydrogen, and magnesium, which are present in the regolith, is not understood. Water vapor has been detected by Chandrayaan-1 and found to vary with latitude. with a maximum at 60–70 degrees, it is possibly generated from the sublimation of water ice in the regolith.
These gases either return into the regolith because of the Moon's gravity or are lost to space, either through solar radiation pressure or, if they are ionized, by being swept away by the solar wind's magnetic field.
Studies of Moon magma samples retrieved by the Apollo missions demonstrate that the Moon had once possessed a relatively thick atmosphere for a period of 70 million years between 3 and 4 billion years ago.
This atmosphere, sourced from gases ejected from lunar volcanic eruptions, was twice the thickness of that of present-day Mars.
The ancient lunar atmosphere was eventually stripped away by solar winds and dissipated into space.
A permanent moon dust cloud exists around the Moon, generated by small particles from comets.
Estimates are 5 tons of comet particles strike the Moon's surface every 24 hours, resulting in the ejection of dust particles.
The dust stays above the Moon approximately 10 minutes, taking 5 minutes to rise, and 5 minutes to fall.
On average, 120 kilograms of dust are present above the Moon, rising up to 100 kilometers above the surface.
Dust counts made by Leidy's Lunar Dust Experiment, LDEX, found particle counts peaked during the Geminid, Quadrantid, Northern Taurid, and Omicron Centaur meteor showers, when the Earth and Moon pass through comet debris.
The lunar dust cloud is asymmetric, being more dense near the boundary between the Moon's day side and night side.
Surface conditions.
Gene Cernan with lunar dust stuck on his suit.
Lunar dust is highly abrasive and can cause damage to human lungs, nervous, and cardiovascular systems.
Ionizing radiation from cosmic rays. The Sun and the resulting neutron radiation produce radiation levels on average of 1.369 millisieverts per day during lunar daytime, which is about 2.6 times more than on the International Space Station with 0.53 millisieverts per day at about 400 kilometers above Earth in orbit, 5 to 10 times more than during a transatlantic flight, 200 times more than on Earth's surface.
For further comparison, radiation on a flight to Mars is about 1.84 millisieverts per day and on Mars on average 0.64 millisieverts per day, with some locations on Mars possibly having levels as low as 0.342 millisieverts per day.
The Moon's axial tilt with respect to the ecliptic is only 1.5427 degrees, much less than the 23.44 degrees of Earth.
Because of this small tilt, the Moon's solar illumination varies much less with season than on Earth, and it allows for the existence of some peaks of eternal light at the Moon's north pole, at the rim of the crater Peary.
The surface is exposed to drastic temperature differences ranging from 140 degrees Celsius to 171 degrees C depending on the solar irradiance.
Because of the lack of atmosphere, temperatures of different areas vary particularly upon whether they are in sunlight or shadow, making topographical details play a decisive role on local surface temperatures.
Parts of many craters, particularly the bottoms of many polar craters, are permanently shadowed. These craters of eternal darkness have extremely low temperatures.
The Lunar Reconnaissance Orbiter measured the lowest summer temperatures in craters at the southern pole at 35 K, 238 degrees C, 397 degrees F, and just 26 K, 247 degrees C, 413 degrees F, close to the winter solstice in the North Polar crater Hermite.
This is the coldest temperature in the solar system ever measured by a spacecraft, colder even than the surface of Pluto.
Blanketed on top of the Moon's crust is a highly comminuted, broken into ever smaller particles, and impact-guarded mostly gray surface layer called regolith, formed by impact processes.
The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder.
The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10, 15 m, 33, 49 feet, in the highlands and 4, 5 m, 13, 16 feet, in the Maria.
Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick.
These extreme conditions, for example, are considered to make it unlikely for spacecraft to harbor bacterial spores at the Moon longer than just one lunar orbit.
Surface features.
Main articles: selenography, lunar terrain, list of lunar features, and list of quadrangles on the Moon.
Astronaut Harrison H.
Schmitt next to a large moon boulder.
The topography of the Moon has been measured with laser altimetry and stereo image analysis.
Its most extensive topographic feature is the giant far-side South Pole, Aitken Basin, some 2,240 kilometers, 1,390 miles, in diameter, the largest crater on the Moon and the second largest confirmed impact crater in the Solar System.
At 13 kilometers, 8.1 mi, deep, its floor is the lowest point on the surface of the Moon.
The highest elevations of the Moon's surface are located directly to the northeast, which might have been thickened by the oblique formation impact of the South Pole, Aitken Basin.
Other large impact basins such as Imbrium, Serenitatis, Chrysium, Smithii, and Orientale possess regionally low elevations and elevated rims.
The far side of the lunar surface is on average about 1.9 kilometers, 1.2 miles, higher than that of the near side.
The discovery of fault-scarp cliffs suggests that the Moon has shrunk by about 90 meters, 300 feet, within the past billion years.
Similar shrinkage features exist on Mercury.
Mare Frigoris, a basin near the North Pole long assumed to be geologically dead, has cracked and shifted.
Since the Moon doesn't have tectonic plates, its tectonic activity is slow and cracks develop as it loses heat.
Volcanic features.
Main article: Volcanism on the Moon.
The names of the main volcanic features: the Maria, blue, and some crater, brown, features of the near side of the Moon.
The main features visible from Earth by the naked eye are dark and relatively featureless lunar plains called Maria, singular mare, Latin for seas, as they were once believed to be filled with water, are vast solidified pools of ancient basaltic lava.
Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water.
The majority of these lava deposits erupted or flowed into the depressions associated with impact basins.
Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria.
Almost all Maria are on the near side of the Moon, and cover 31% of the surface of the near side compared with 2% of the far side.
This is likely due to a concentration of heat-producing elements under the crust on the near side, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt.
Most of the Moon's mare basalts erupted during the Imbrian period, 3.7 billion years ago, though some being as young as 1.2 billion years and as old as 4.2 billion years.
Old hardened lava flows of mare Imbrium forming wrinkle ridges.
In 2006, a study of Ina, a tiny depression in Lacus Felicitatis, found jagged, relatively dust-free features that, because of the lack of erosion by infalling debris, appear to be only 2 million years old.
Mooncakes and releases of gas indicate continued lunar activity.
Evidence of recent lunar volcanism has been identified at 70 irregular mare patches, some less than 50 million years old.
This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side where the deep crust is substantially warmer because of the greater concentration of radioactive elements.
Evidence has been found for 10 million years old basaltic volcanism within the crater Lowell, inside the Orientale Basin.
Some combination of an initially hotter mantle and local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities on the far side in the Orientale Basin.
The lighter-colored regions of the Moon are called Terrae, or more commonly highlands, because they are higher than most Maria.
They have been radiometrically dated to having formed 4.4 billion years ago, and may represent plagioclase cumulates of the lunar magma ocean.
In contrast to Earth, no major lunar mountains are believed to have formed as a result of tectonic events.
The concentration of Maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after the Moon's formation.
Alternatively, it may be a consequence of asymmetrical tidal heating when the Moon was much closer to the Earth.
Impact craters.
Further information, list of craters on the Moon.
A grey, many-ridged surface from high above.
The largest feature is a circular ring structure with high-walled sides and a lower central peak. The entire surface out to the horizon is filled with similar structures that are smaller and overlapping.
A view of a 3-kilometre deep larger crater Daedalus on the Moon's far side.
A major geologic process that has affected the Moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface.
There are estimated to be roughly 300,000 craters wider than 1 kilometre, 0.6 mi, on the Moon's near side.
The lunar geologic timescale is based on the most prominent impact events, including Nectaris, Imbrium, and Orion Tail, structures characterized by multiple rings of uplifted material, between hundreds and thousands of kilometers in diameter and associated with a broad apron